Right now, as you're watching this, advanced hackers are stealing trillions of gigabytes of encrypted data. They can't read it today, but they're saving it for the one day in the next 10 years when a quantum computer will be able to crack it all in minutes. This is the story of the biggest data heist in history, and it's happening in plain sight. Your phone is pretty safe. Every time you send a WhatsApp message, buy something online, or unlock your phone with your face, your data is being protected by cryptography. Think of cryptography as super strong math locks, the kind of locks that would take a regular computer longer than the age of the universe to crack. That's why we can message friends, bank online, or store cat memes without worrying that someone's peeking inside. But this math magic has one big weakness. It wasn't built to fight quantum computers. Now picture this. You wake up tomorrow morning, grab your phone, and boom, your bank app is empty, your chats are exposed, and someone in another country is posting memes from your Instagram account. No, it's not your ex. It's a quantum computer. And trust me, if you think regular hackers are scary, quantum computers are like hackers on steroids. They don't just pick locks. They melt the entire lock into butter. But here's the good news. There's a superhero coming to the rescue. It's called Post-Quantum Cryptography. And in this video, I'll explain why it's literally the only way your phone and everything on it will stay secure in the future. Now, before you start picturing Terminator-style robots hacking your WhatsApp, let's break down what quantum computing is and why it's such a game changer for cybersecurity. In the world we know today, our computers use bits, electrical signals that are either a 0 or a 1. That's how all your digital information is stored and processed. Quantum computers, however, use qubits, and qubits are wild. Thanks to principles like superposition and entanglement, a qubit can be a 0, a 1, or both at the same time. This isn't just a technical detail, it's a revolutionary leap in processing power. Imagine a computer that can explore millions of possibilities simultaneously, rather than one after another. That's the power of quantum. For certain types of problems, specifically the kind of mathematical problems that current encryption relies on, quantum computers are going to be astronomically faster than even the most powerful supercomputers we have today. And this is where the danger lies. The encryption that protects your phone, your bank account, your medical records. It all hinges on the idea that certain mathematical problems are incredibly difficult, practically impossible, for classical computers to solve within a reasonable time frame. We're talking about factoring massive numbers or solving discrete logarithms. These problems would take a classical computer billions of years to crack. But for a sufficiently powerful quantum computer, these problems could be solved in minutes, hours, or days. This isn't theoretical, it's a fundamental property of quantum mechanics. Algorithms like Shor's algorithm, discovered by Peter Shor in 1994, show us exactly how a quantum computer could break widely used public key cryptographic systems like RSA and elliptic curve cryptography (ECC). And RSA and ECC are the backbone of internet security. They're what protect your online shopping, your secure websites. Look for that little padlock in your browser. And yes, the secure communication channels on your phone. Now, you might be thinking, quantum computers aren't here yet, right? You'd be largely correct. Fully error-corrected, large-scale quantum computers capable of running Shor's algorithm are still some years away from being widely available. Estimates vary, but many experts predict they could emerge within the next 10 to 20 years, possibly sooner. But here's the terrifying thing. The harvest now, decrypt later threat. Adversaries, whether they are state actors, sophisticated criminal organizations, or even just future hackers, can today intercept and store vast amounts of encrypted data. They can collect your emails, your financial transactions, your private messages, anything that travels over insecure channels. This isn't a passive threat. It's an active global intelligence operation. Think of it as a new kind of Cold War. Nation-state intelligence agencies are currently using their vast resources to vacuum up enormous amounts of encrypted data from undersea fiber optic cables, satellite links, and corporate networks. They are building massive data centers filled with information they can't yet read. They're targeting data with a long shelf life, information that will still be valuable a decade from now. This includes diplomatic cables, classified military communications, long-term corporate trade secrets like pharmaceutical formulas or next-generation aircraft designs, and even sensitive government personnel files. They are making a bet that any secret encrypted with today's technology is simply a temporary secret. Once they have a powerful enough quantum computer, they can go back to this massive stockpile of stolen data and decrypt it all at once, creating a catastrophic global intelligence failure. The data you send today is being harvested for the quantum world of tomorrow. They can't decrypt it today, but once a powerful quantum computer becomes available, they could theoretically take all that stored encrypted data and decrypt it, revealing secrets from the past that were thought to be forever safe. This means your private communications from today could be exposed in the future. This isn't just future secrets, it's the long-term confidentiality of the information you consider private today. So, how secure are our phones today? Pretty secure, thanks to robust cryptographic standards. When you browse a secure website, make a video call, or send an encrypted message, your phone is constantly performing complex mathematical operations to encrypt and decrypt data. This typically involves a combination of public key cryptography like RSA or ECC for key exchange and digital signatures, and symmetric key cryptography like AES for bulk data encryption. Symmetric key algorithms are generally considered more resistant to quantum attacks, but the public key components that secure the exchange of those symmetric keys are vulnerable. So, even if your actual message content is encrypted with an algorithm that might withstand quantum attacks, the process of establishing that secure connection, the initial handshake, is very much at risk. If that handshake can be broken, the entire communication is compromised. This is where post-quantum cryptography, or PQC, comes in. PQC refers to new cryptographic algorithms that are designed to be resistant to attacks by both classical and quantum computers. The goal is to develop encryption methods that are so mathematically complex, even a future quantum supercomputer would struggle to break them within a practical time frame. The good news is, brilliant minds around the world have been working on this for years. Organizations like the National Institute of Standards and Technology, NIST, in the United States have been leading a global competition to standardize these new algorithms. This process has involved rigorous analysis, peer review, and multiple rounds of refinement, much like an Olympic selection process for algorithms. After years of evaluation, NIST recently announced the first set of algorithms chosen for standardization. These include Crystal's Kyber for key establishment, essentially setting up a secure channel. Crystal's dilithium for digital signatures, verifying the authenticity of messages and users. So why are these new algorithms quantum resistant? It's because they are based on entirely different types of mathematical problems that are believed to be hard for both classical and quantum computers. The most promising field is called lattice-based cryptography, which is what Kyber and dilithium are built on. Here's a simple analogy. Breaking current encryption is like finding the prime factors of a huge number, a task Shor's algorithm is perfect for. Breaking lattice-based encryption is like being dropped into an infinitely vast, foggy, multidimensional grid of points and being asked to find the single point closest to where you started. It's a needle in a haystack problem of almost unimaginable scale and complexity. The unique geometric structure of the haystack, the lattice, is what makes it so difficult to navigate. Even a quantum computer, which can check many places at once, gets hopelessly lost. By switching to these new hard problems, PQC builds a new kind of digital lock that quantum computers simply don't have the right key for. We're talking about things like lattice-based cryptography, code-based cryptography, and multivariate polynomial cryptography. Don't worry, you don't need to be a math genius to understand the implications. So, if these new algorithms exist, why isn't your phone quantum safe today? Well, migrating the entire digital infrastructure of the world to new cryptographic standards is a monumental task. It's not like simply updating an app. Here's what needs to happen: standardization and development. This is largely underway, with NIST leading the charge. Other organizations are also contributing to research and development. Implementation: software developers, operating system designers, Apple, Google, hardware manufacturers, Qualcomm, Samsung, and service providers, your telecom company, your banking app, need to integrate these new algorithms into their products and services. This means new code, new hardware components, and extensive testing to ensure they are robust, efficient, and compatible. Migration: billions of devices, servers, and systems around the world need to be updated. This will be a gradual process, likely starting with critical infrastructure and then trickling down to consumer devices. Think about how long it takes for a new version of Android or iOS to roll out globally and be adopted by users. This is even more complex. For your phone, this means that future versions of iOS and Android will need to incorporate PQC algorithms. Chipmakers will need to design new secure enclaves and processors that can efficiently handle the computations required for these new, often more computationally intensive, algorithms. App developers will then need to ensure their applications can leverage these new quantum-safe layers. It's a massive undertaking, but the good news is that work has already begun. Companies are starting to experiment with hybrid approaches, where both classical and post-quantum algorithms are used simultaneously, providing a fallback in case one of the new PQC algorithms is later found to have vulnerabilities. This is a cautious and smart approach to a complex transition. It's not just your phone itself, it's the entire ecosystem it connects to. Your mobile network, the servers that host your favorite apps, the cloud infrastructure where your data lives. All of these need to become quantum safe. So what does this mean for you, the everyday phone user? For now, your phone is still largely secure against classical attacks. You don't need to panic and throw your smartphone into a river. However, it's crucial to stay informed. As PQC standards solidify and implementations begin to roll out, expect to see software updates. Future operating system updates, iOS, Android, will likely include PQC capabilities. Keep your phone updated. New hardware. Next-generation smartphones will probably boast quantum-safe chips or features, making PQC processing more efficient. Industry collaboration. Governments, tech companies, and cybersecurity experts will continue to collaborate to ensure a smooth and secure transition. Your primary role remains the same. Practice good cybersecurity hygiene. Use strong, unique passwords. Enable two-factor authentication. Be careful of phishing attempts, and always keep your software updated. These best practices will continue to be your first line of defense, even as the underlying cryptography evolves. The arrival of practical quantum computers isn't a matter of if, but when. And when they do arrive, they will be powerful enough to dismantle our current cryptographic defenses. It's a certainty. This is why post-quantum cryptography isn't just an option. It's an absolute necessity. It is the only viable path forward to ensure that our digital communications, our personal data, and our societal infrastructure remain secure in a quantum-powered world. The race is on to build a quantum-safe future, and your phone, that indispensable device in your pocket, is at the heart of it. It's a complex journey, but one we must embark on to protect our digital spaces for generations to come. If you're ready to secure your business before the quantum storm hits, reach out to the experts at Tileris. We'll work with you to design a personalized security strategy, and you can even request a demo of our AI cybersecurity agents in action. Your data deserves more than ordinary protection. With Tileris, you can stay ahead of tomorrow's threats today. What are your thoughts on quantum computing and its impact on security? Let me know in the comments below. Don't forget to like this video, subscribe for more deep dives into tech and security, and hit that notification bell so you don't miss our next upload. Thanks for watching, and I'll see you in the next one. If you found this video interesting, please share it so more people can see it.